I'm gonna sort of end with the support vector classification because this is one that I don't think was used in the original paper, and I think maybe my next video will be about the original paper and some of the results. So let's take a look though. So again, I am doing Bayesian optimization, and for the SVC, I've decided that I'm using the kernel, the RBF, the radial basis function kernel, so that doesn't need to be anything different. But the C, the cost, and the gamma are, which is sort of the width parameter of the radial basis function, is something that's still up for grabs. So I'm gonna just try to optimize to find the best C and best gamma. So again, how do I do that? I'm doing cross-val score from sklearn of this particular regressor over the entire data set using the repeated stratified k-fold scheme that we used before. So maybe I'll just put global RSKF here just to make sure that we're using the same one. And the scoring again is the is MCC, the Matthews correlation coefficient. And I want to see what values give me the best support vector machine, right? And what gives me the best overall scores, the best average scores. So for C, I could probably put this as less than 1. Maybe I'll do that, 0.8 or something, 0.5. You can really start it from anything really low, but sometimes you'll get something like high, like you'll need 50 or 100, but it's pretty rare. It's usually like the default value is 1. So, worst comes to worst, you just sort of try around like between 0 and 10 or 0 and 5. And if you feel like you're doing well and it's pushing to the higher ranges, like if you tried 0 to 5 and it kept being 5, then maybe you should try 5 to 10 as well, or 0 to 10. The gamma usually is, well, the gamma is usually sometimes when you do the scale, I think it takes 1 divided by the number of features or something like that. So 1 over 16. So you expect it to be like zero point 0 something, or maybe I'll do this a little bit lower, but it's probably not going to be that much higher than 1. So I'm just going to run this here. Again, this is you're optimizing this function with these parameters, and I'm doing 2 initial points and 20 iterations just like before. And this one is super fast. You can see here there's no purple one because the first one was the best. So basically it's not ever beat what it started with, which is, I mean, it's not a bad sign, but it's kind of disappointing sometimes. Anyway, there's not a huge, and you can see there is some kind of variance here, but there's a lot of scores that are kind of consistently in the 93 range, 92, 93, 94 range. So what do we have then? The best parameters are going to be C is about 39.29 and gamma is 0.65. And so I'm going to create a SVC model with those parameters, fit it on the entire data set, and use the cross-validation to see how good it does. And you'll see that it's got a cross-val score of 949, which I think is maybe above the random forest one. And again, it makes an error of having 3 false positives. So what was the random forest level? So let's go back here. Random forest, it's 947 was what it got here. So SVC is technically, in terms of the cross-validation, there's an argument that it's just as good, if not better, than the random forest one, right? So it's 949 as opposed to 947, and it doesn't make any more errors than random forest. So let's take a look at its SHAP values. So this is not a tree, right? Out of all the algorithms we've done in terms of this Bayesian stuff, I haven't done anything other than trees, and so you can use SHAP.TreeExplainer, but when you're using a sort of a general sklearn algorithm like that's not a tree, then you're going to need kernel explainer. So SHAP has different explainers for different types of models. There's one for deep learning ones like Keras models, and tree is for any sklearn tree one, and or sklearn compatible tree type regressor. And kernel is just sort of like the general one. It's not kernel because for RBF or anything. It's just the name of it, I think. And Here though, you have to write reg predict because um, for this one, like this needs to be a callable thing. So if you write just reg, it doesn't work because it has to be a function that a callable function that can predict actual values. So for some reason here, you have to remember it's not reg that predicts the value so much as it is reg predict, the function that predicts the values you want. So the data is going to be a sample. So I forgot here that I'm doing a sample of 30 just because this takes a little bit longer. So for the sake of speed, I'm only using 30 of, yes, of 520. So I'm using 30 samples, and so I'm going to use that. And I'm going to then use SHAP values as the same. So this is the same. I'm using the explainer to, and here are the SHAP values of this particular sample. And then I'm going to go over here and do the summary plot, which again will give me a bar graph that will show you exactly what features are important. And this will sort of show you in this SVC model what's considered important. So you can see here that it's taking about 1 second, 1 second per 1 item per second. So basically 30 takes you like 30 seconds or 28 seconds or whatever. And so that's why I didn't want to do 500 because that would have taken like 8 minutes or something. So here again, so again, this may not be as accurate because we're only dealing with a sample of 30, but polydipsia here is above polyuria, but they are still the top two. Gender and age, again, appear. So, gender and age have always sort of been in the top, but in certain models, it's like number 3 and 4, and including this one. So, and in terms of retaining features or feature selection, then I think there's a good argument to keep gender and age in there. Obesity, again, is one of the lowest ones. Weakness is already, again, one of the lowest ones. Some of these ones, like paresis, sometimes is at the bottom. Sometimes here it's sort of not quite at the very bottom. So, this one, depending on the model, you may want to keep this as well. But all I can say is you definitely want polydipsia and uria, gender and age, and you definitely could live without obesity and weakness. Everything else, though, really depends on the model. And as we saw before, this SVC model just gives you the sort of same, confusion matrix. So there's nothing different in that. But yeah, it looks like it could be slightly better than the random forest goes. So that's the end of this video.